So concepts of limiting reaction, theoretical yield, actual yield, percent yield, these are very important in real life situations like manufacturing. You need to know how much raw ingredients you need to make the amount of stuff that you've committed to making. You want to evaluate your percent yield so that you can see, are we making good use of all of our reactants, or is our process not efficient? Could we make it better? 100% yield would be awesome, but it's not attainable. But the closer you get to that, the more money you're going to make. When you're making chemicals, some of the reactants are much more expensive than other reactants. And so you want to make sure that you use up the expensive one and that you have excess of the other things that are less expensive. In the lab, we measure things in grams instead of in moles. And so we need to be able to do these limiting reactant calculations using grams. It's just a little 2 extra steps of converting from grams to moles at the beginning and from moles back to grams at the end. So let's do an example. So making sodium chloride out of sodium and chlorine. If we have 53.2 grams of sodium, 65.8 grams of chlorine, what are the limiting reactant and the theoretical yield for this process? So we've got our chemical equation. We're going to put the numbers under the element or the formulas. So 53.2 grams of that, 65.8 grams of that, and the theoretical yield. Here there's only one product, so that must be what they're asking us for. We want to know how much of that in grams. So we've got amounts for both reactants. We need to do 2 calculations. This is not the only way to solve these problems, but it's the most straightforward. So if you can do it another way, that's fine, but I'm just going to stick to one method. So what is our full-blown path for stoichiometry? Grams to moles to moles to grams, right? So grams to moles to grams. So what we need to do is we need to take sodium, grams of sodium to moles of product, sodium chloride, 2 grams of sodium chloride. And then we need to do a similar process with the chlorine. So 53.2 grams of sodium. Grams to moles to grams. If you need to write the path, grams of sodium to moles of sodium sodium chloride to grams of sodium chloride, by all means, write it. I don't have a lot of room on this slide, so I'm going to kind of just abbreviate it. I've got it up there. Grams of sodium, so that cancels. Moles of sodium, so that cancels. Moles of sodium chloride, so that cancels. I like the middle one because it's easy. I look up here, 2 moles of sodium, 2 moles of sodium chloride. Put a 2 there, 2 on the bottom. I need the molar mass of sodium. Well, this is easier because it's an element. I don't actually have to calculate it. I just look it up on the periodic table. 1 mole of sodium weighs 22.99 grams. Sodium chloride, I do need to calculate that one. It's sodium 22.99 plus chlorine 35.45. I think that's 58.44. Yeah, 58.44. So 1 mole of sodium chloride weighs 58.44 grams. So I'm going to start out with 53.2 times the top, divide by the bottom. Times the top, divide by the bottom. The 2's cancel out, but you can multiply by them and it's fine. Times the top, divide by the bottom. My answer should have 3 significant figures. So 135.23 grams of sodium chloride could be made. I don't know if that's my final answer or not, because maybe this amount of chlorine will make less. So I have to do another calculation. It's very, very similar. So 65.8 grams of chlorine. Grams to moles to moles to grams. So grams of chlorine to moles of chlorine to moles of the product. Remember, we're trying to end up at mass of the same thing. Sometimes students get off track and they just get a little crazy calculating, and they calculate moles of sodium from moles of chlorine, and we're going to the same place. Moles of sodium chloride to grams of sodium chloride. Put units in the denominator to cancel the previous unit. Got all the units in place, now I go for numbers. The mole ratio comes from the balanced chemical equation. 1 mole of chlorine makes 2 moles of sodium chloride. So I get 2 moles of sodium chloride from every 1 mole of chlorine. This last one is also easy because I already did this. The last fraction is going to be the same. So that's convenient. 58.44 grams per mole. And then here I need the molar mass of chlorine, which is just 2 times 35.45, which I believe is 70.9. No. I lied. 35.45 times 2. No, I didn't lie. It is 70.9. I doubted myself. So 1 mole of chlorine weighs 70.90 grams. I put the 0 in here because this should have 4 significant figures. My calculator didn't put the 0 there, but I know better. So 65.8 times 1 divided by 70.90 times 2 divided by 1 times 58.44 divided by 1 equals, and this should also have 3 sig figs. That would round to 108 grams. Any questions? Yes? So the question is, do you have to go to grams? Usually the question, like on an exam, the question is going to be more specific. Here it's asking for theoretical yield. It's not specifying moles. It's not a clear question. So if it doesn't specify, yeah, you could stop at moles. You can determine the limiting reactant by looking at the number of moles of each and picking the smaller. That'll tell you which is the limiting reactant. But then if you need to figure out the mass, you're going to have to convert it anyway. So what I think is more straightforward is to just do both of the calculations all the way, because all you're saving is multiplying by this number. You're still going to need to figure out what it is. This way you can just calculate and pick the smaller and be done. So this isn't the only way, but I think it's more straightforward. Does that answer your question? That's a good question. This seems time consuming. How much time are you going to be given on an exam? I do take into account that these questions take longer to answer. And so a question like this exam is probably going to be more like 25 or 30 questions instead of 50, because these questions do take longer. Part of being proficient in chemistry is being able to do the problems in a reasonable amount of time. And so that is an issue. What we often do to speed things up for an exam is, instead of making you calculate molar masses, we'll give you the molar masses. So all you have to do is plug them into the equation. In a different problem, I'll test you on, do you know how to calculate molar masses? So we'll separate that into steps. At most, there would be one question that's a limiting reactant problem with grams. It's more likely that there would be limiting reactant problems with moles, like the one we did before, where you don't have to do the grams at the end. That is intended to be a shorter, easier problem. Unfortunately, students freak out and do crazy things and make it harder and get the answer wrong because they try to go moles to grams to moles, which you can't do. Did that answer your question? Any other questions? Are we done with this problem? No, we're not done yet. We have to pick an answer. We've got two numbers here. The theoretical yield is the smaller one. 135 is larger, so this is the smaller one. That's the theoretical yield. Which is the limiting reactant, sodium or chlorine? Chlorine. Because as we go from this back, what we see is that it was chlorine that gave us the smallest amount. So chlorine is the limiting reactant. Cl2 is limiting. Can't write. We can't tell just by looking at these masses which one is limiting, just like with the pancake recipe, because the relationships are more complicated, right? Here, there's actually more chlorine by mass than sodium, and yet this is the one that runs out first. So you can't just look at them and tell. Any questions? Let's do another one. Ammonia can be synthesized by this reaction. What maximum amount of ammonia in grams can be synthesized from 25.2 grams of nitrogen and 8.42 grams of hydrogen? So again, take the numbers and write them under the formulas. So 25.2 grams of nitrogen and 8.42 grams of hydrogen. Doesn't say anything in the question about limiting reactant or theoretical yield or anything. It's just saying how much can we make. We can tell this is a limiting reactant problem because we've got two masses for the reactants. We're wanting to know amount of ammonia in grams, so question mark grams. Two amounts, two calculations. Grams to moles to moles to grams. I like to start with the first one, 8.42 grams of hydrogen. grams to moles. To moles. Moles of what? The moles of the thing with the question mark. Moles of NH3. Grams to moles to grams of NH3. I put the other units in so they cancel out. Actually look at your units when you're canceling them out, because sometimes we have this wishful unit canceling where I wish they would cancel out, so I just cross them off and hope for the best. They actually need to cancel out. Mole ratio, 2 moles of ammonia, 3 moles of hydrogen. We need a molar mass here, 2 times the mass of hydrogen, so 1 mole times 2.016. When you're calculating this molar mass, you're only looking at the chemical formula. You are not looking at the coefficient in front. The coefficient comes in the mole ratio. It is not included in the mass of the mole of 1 mole of the thing. Over here, you would calculate the molar mass of ammonia. This is 17.043. So then you do the math. 8.42 divided by 2.016 times 2 divided by 3 times 17.043 equals. My starting number had 3 significant figures, so I want to keep 3 here. So there's a mass. So that was the hydrogen. I'm going to do the same process with the nitrogen. 25.2 grams of nitrogen. Grams to moles to grams. So moles of nitrogen, moles of ammonia, grams of ammonia. Put units in the denominator so they cancel out. I've got the units in place, so do the numbers. This last one is the same. It's convenient. If it isn't the same, then something went wrong in your path, or you left the path. Ratios here, 2 moles of ammonia to 1 mole of nitrogen. 2 moles of ammonia, 1 mole of nitrogen. Here I need the molar mass of nitrogen. It's 2 times the mass of nitrogen. It's 28.02. 25.2 divided by 28.02 times 2 times 17.043. I think it's actually supposed to be 034. I'm going to ignore that for right now. Let's see, 3 times 1.008 plus 14.01. Yeah, it's supposed to be 34. Dang it. So I screwed that up. Whew. That was just screwed up even more. That's what happens when you try to do things from your memory. It's 3-4. This is 3-4. Which of these is smaller? Yeah, the nitrogen one. This is the smaller one. So I'm going to fix it because I got the wrong number. 25. 30.639? Yeah. 30.639. Thank you. So this small difference here only made a very small difference here, so that's good, but still This would round to 30.7, but the actual would be 30.6. So 30.6 grams of ammonia. That's our answer. Any questions? You need to do enough of these problems that you can do them fairly quickly, that you don't have to puzzle out each individual step. Okay, here's another one. This is reaction that's used to make to get iron from iron ore. It uses carbon monoxide. So the reaction of 185 grams of the iron oxide with 95.3 grams of carbon monoxide produces 87.4 grams of iron. Find the limiting reactant, theoretical yield, and percent yield. Okay, we read the problem. Now we're going to organize our numbers. So I've got 185 grams of the oxide, and it says 95.3 grams of carbon monoxide, and it produces 87.4 grams of iron. They gave me three numbers. They're asking for the theoretical yield. What we've been doing is we take the mass of one reactant and we find the mass of product. Take the mass of the other reactant, find the mass of product, and we pick the smaller. Why do we have a mass of product? This is the actual yield. We need this for the percentage, the percent yield. They had to give this to us because there's no way for us to know what the actual yield is. This is the actual yield. We do need to calculate the percent yield. I'm sorry, the theoretical yield. So we're still looking for how many grams of iron can be made. So 185 grams of Fe2O3. Grams to moles to moles to grams. So grams to moles to moles of iron to grams of iron. Does this get tedious sometimes? Yeah, it does. Moles of iron. 2 moles of iron. 1 mole of Fe2O3. This molar mass is the easiest one. Tell me if I'm wrong, but I'm pretty sure it's 55.85 molar mass of iron. You guys can see the periodic table better than I can. Okay, thanks. And then we need to calculate this one. We're running out of time, so I'm not going to write it out. 2 times 55.85 plus 3 times 16, 159.7. 1 mole of iron oxide weighs that. So when I do this calculation, I get 129.39 grams of iron. Should have 3 sig figs. Here it's more important to carry those 2 extra digits because this is not the final answer. I need to use it to calculate the percent yield. So that's one possible theoretical yield. I also need to do similar calculation with this. It's a 95.3 grams of carbon monoxide. Don't get that confused with cobalt. To moles of carbon monoxide, to grams of iron. No. Grams to moles to grams. Moles of iron. I was wanting to be done sooner. Grams of iron. Moles of iron come down there. Cancel those out. Moles of CO. Canceling out. Grams of CO. Canceling out. Numbers on the last one are the same because it's the molar mass of iron. Mole ratio, 2 moles of iron, 3 moles of CO. 2 moles of iron, 3 moles of CO. Then here I need the molar mass of carbon monoxide is 12.01 plus 16, 28.01. That's a G. 95.3 divided by 28.01 times 2 divided by 3 times 55.85 equals 126.68 grams of iron. So let's look at the question again. Find the limiting reactant, theoretical yield, and percent yield. So what's our theoretical yield? It's the smaller one. It's this one. So to round this to 3 sig figs, this is 5 or greater, I round up. 127 grams iron equals the theoretical yield. What's the limiting reactant? Carbon monoxide. That's the limiting reactant. Okay? This is the stuff that ran out, that gave us the smaller amount. And now percent yield. So this is where it's a little different. So percent yield equals the actual yield divided by the theoretical yield times 100%. So the actual yield was given to us, 87.4 grams. We just calculated the theoretical yield. I want to use this one because I want to avoid rounding errors. So I'm going to use 126.68 times 100. We got 87.4 divided by 126.68 times 100. Three sig figs, 3 sig figs. This should have 3 sig figs. So the next digit is 9. It's 5 or larger, so I have to round up. So this 9 rounds up to a 10, a 0, and then that rounds up to a 9, and so I end up with 69.0% is my yield. Any questions? Could the yield be like 1,000%? If the yield was 1,000%, that would be like crazy, crazy wrong. You'll never have a problem given to you where that would happen. If you have a yield like that in lab, you did something wrong in the calculation. We occasionally get something like 150% in lab because people don't know what they're doing, right? And so they make mistakes. You could have a problem where it's going to be like 105%, but yeah, 1,000% no.